This exercise discusses the electric potential due to a charged conducting sphere. Remember that the electric field is equal to zero inside a conducting sphere. So let me draw this. So we have do that. Change the color, black. So that's a conducting sphere. It has a radius r, and everywhere inside the electric field is equal to zero. And outside it is of course 1 over r square. So this is a positively charged sphere. So that's charge q that's given to us. All the charges for a conductor always is on the surface of the conductor. And we know that electric field, if we were to express this explicitly, is equal to zero if you're inside the sphere. So let me say this is inside the sphere. And it is equal to k times q over r square in the direction pointing radially outside when you're outside the sphere. That means to say that the force, electric field is related to the force. So force acting on another charge q would also be equal to zero inside. It is zero inside, and outside is k times small q over capital Q over r square. So if you had a charge inside, it will just float around when there is no force acting on it. There is no motion associated with it. So there is no electric force on a positive charge in here, even though there are charges on the outside of the sphere, they don't uh, tend to do anything to another charge inside because electric field is zero. So if there is no force, there is no work done to move a charge inside, so it moves freely. That means to say that the electric potential energy is zero in, or it is not zero. The force is zero, so that means the potential energy must be the same. There is no work needed to move at all. So that means change in potential will be equal to zero. That means let me write that down. So force is zero. That means change in potential would be equal to zero. That means U2, U final minus will be the same as U initial. That means to say that the electric potential energy to move from any point, it doesn't have to be on the surface and inside, anywhere inside has to be the same. So once you know the electric potential on the surface, we know that the electric potential at the center, or for that matter anywhere on the sphere, has to be the same because change in potential has to be zero. So that means the potential has to be constant uh, at any of these points. So what we can say is an electric potential energy is the same as, or change in electric potential energy is the change as same as q times the change in electric potential. So if change in potential energy is zero, so you say change in potential also is zero. So v is equal to zero inside the sphere. That implies that v is a constant. If change has to be zero, so v, this should not change. V is a constant inside the sphere. V is a constant also means that maybe it could be zero, but but then it also has to be the same as on the surface. So we deduce using all these arguments that the electric potential due to a sphere is equal to the electric potential on the surface of the sphere when it is inside. So it is not zero. Whatever is the electric potential on the surface, that's what will be the, the electric potential when it is inside. And when it is outside, it is simply KQ over R when it is outside. So that's your equation. And what is V surface? What's the electric potential on the surface? That's, you just evaluate it at the value of the surface. So that's KQ over R. I can write that as KQ over R, but then uh, this is more, comes out more explicit that this is a constant value which is decided by the value at the surface. So to answer the questions, we just have to figure out whether we are inside the sphere or outside the sphere. What is the electric potential at the center of the conducting sphere? That's inside. So center is inside. And once it is inside, we know that V has to be equal to KQ over the on the surface. So that's the radius of the sphere. This is not the distance from the center. This is the radius of the sphere. So let's calculate that immediately. So that's to two sig digits. It's 9.9 into 10 raised to 9. Q is plus 2.0 into 10 raised to minus 6 and divided by the radius, which is 1.0 into 10 raised to minus 2. So that gives us, so 9 into 2 is 18, and 18 into 10 raised to 5. So that's 1.8 into 10 raised to 6 volts. That's volts per meter. So let me check again. So that's 10 raised to 3, 10 raised to 5, and I need 1 to make 18 into 1.8. So that's 1.8 into 10 raised to 6 volts on the surface of the sphere, also on anywhere inside. So specifically in part A, we are asking at the center of the sphere. Part B, again, we ask, are we outside or inside? Calculate the electric potential at a point 0.25 centimeters. The radius is 1 centimeter. So that's somewhere here, quarter radius. But again, the only thing that's crucial is it inside or outside? If it is inside, again, we would be 1.8 into 10 raised to 6 volts. There is no work needed to move from the center to 0.25 centimeters because there is no force acting on the charge inside a conducting sphere. Part C, calculate the electric potential on the surface of the conducting sphere. On the surface, that's right on the border. It doesn't matter whether we use this expression or that. So this is on the surface, which is what we already calculated. We again say this is 1.8 into 10 raised to 6 volts. In part D, calculate the electric potential at a 0.5 centimeters from the center of the conducting sphere. And now we are outside. So in part D, we are finally outside the sphere. And we say the electric potential now would be KQ over the distance from the center, which is given to be 5 centimeters. So this will be 9.0 into 10 raised to 9. The charge is 2.0 into 10 raised to minus 6 divided by the distance, which is 5 centimeters. So it's 5.0 into 10 raised to minus 2. So that will be 1.8 divided by 5. So that will be 3.6 into 10 raised to 5 volts. which is smaller. That means in terms of 10 raised to 6, I can write this as 0.36 into 10 raised to 6 volts, which clarifies that this is smaller than the quantity on the surface. So it's a 1 over r function. So as you go farther and farther, it gets smaller and smaller. The main idea here is that inside the conducting sphere, the electric potential is a constant, and it is exactly the same as the quantity that's on the surface. Let me stop sharing and then stop the recording.